We are starting this first parallel session, and we are very pleased to welcome on stage my colleague, José ALVES, working as in Transvalor in our development team. And this is going to be a joint presentation together with Sergio ACEVADO from the University of Osnabrück, and more specifically, the laboratory LUW for Forming Technology and Machine Tool Laboratory. So this presentation is about electrical upsetting. You have seen this morning in the roadmap that this is one process where we want to extend our capacity. So you will have a full and complete overview of our possibility in this matter. José?
So thank you very much, Stefan, for your presentation. Today we'll present, this is a continuation of a project that started 2 years ago in a partnership between Transvalor, the Osnabrück University of Technology, and IFU-Tech in Germany, regarding the electric upsetting process. So for this presentation, first I will do an introduction about what is the electric forming process, and then we'll continue to explain the study case we have used for this last phase of the project. Then I will explain some of the updates, the two main updates we have integrated into the simulation process. Then my colleague Sergio will explain the experimental part of the project, and finally some of the latest results. So, as most of you know, today's manufacturing industry is constantly pursuing to improve cost and consumption efficiency in manufacturing process. And we're frequently faced with the need of finding a balance between increasing the performance and decreasing the cost of the process. And in metal forming industry, this is linked with the limitations posed by the elastic spring back and the low forming limits. Thus, we require for some innovative techniques to bypass these limitations. The electroforming process consists, as was explained this morning, in passing an electric current directly through the billets. And we are going to increase the temperature of the billet in such a way that it would allow us to access almost limitless formability by increasing the temperature in between the grains. Thus, we will allow it to deform without creating cracks in the part that is shown here in this figure. So, there are three main building blocks in order to describe the physics behind the process. The electric current flow, distribution, the heat transfer phenomena, and the mechanics. From the charge conservation equation, we'll compute the electric current. And from here, we'll obtain the Joule heating effect that will allow us to compute the temperature evolution. From the temperature, we'll modify the material. We'll also compute the mechanics, and all these blocks will interact with each other. And now this is all integrated in a natural way within the forge solver. So now I will talk about the study case we have decided to use for this phase. What we want to do is to optimize, to deform a tube and optimize the shape in order to minimize the material we are going to machine for the last step of the process. So the idea is to focus around an intermediate shape, an intermediate state of the process, and obtain a final shape as close as possible to this one, and so that we know that we don't need to take out too much material. Sorry. So in order to describe the process, we are going to define our geometries. We are going to make use of the formal bodies like the anvil, the die, the clamp, and the billet. These are our computational domains. We also have some rigid bodies in order to define the boundary conditions for the electricity, the thermal change, and also the mechanics, of course. And so once these geometries are defined, we are going to measure with volumetric finite elements. For the tools, that they're also deformable, we are going to use large elements because we do not expect large temperature or deformation gradients in them. And we're going to focus most of the meshing at the head of the billet because we know that this is the section that is going to suffer most of the deformation and increase in temperature. And then we also make use of the automatic remeshing technique in Forge in order to allow for these large deformations. In order to describe our material, we have decided to make use of the GMAT Pro software, with whom we have a strong partnership, as you have already seen this morning. The software will allow us to describe the rheological data by giving just as input the chemical composition, as you can see here, of our material. So we get all the thermophysical data and the rheological data from GMAT Pro. And we need this because we are going to largely deform our part, and at the same time we're going to heat it up from room temperature to more than 1,000 degrees. And there's a little bibliography that can describe this large range of deformation and temperature. So now let's talk about the updates we have introduced in this last phase of the project. The first key point, it's related to the contact, the electric contact specifically. One of the critical aspects is that we know that between these two bodies, between the bodies in contact, there's going to be an electric contact resistivity. And this resistivity will produce a jump in the electric potential. From here, we're going to compute, or we are going to obtain power, heat power, just at the level of the surface that is critical to describe the heating of the part. From our research, we have found that we can summarize this phenomenon or this physics with two principles. First, we have the effective area. We know that the effective area for computing this electric contact is smaller than the actual area we can see because of the rugosity in between the parts. But this rugosity is also going to be deformed due to the pressure and the temperature. And also, we know that the properties at the surface may be different from the bulk material, or there could be film and oil, something covering the oxides that are going to produce. So these are modeled with film resistance. All of this is now integrated with this new formulation we have introduced into the solver. Here, it was supposed to be an animation, sorry. So here we can see how this law, it's going to modify, depending on the pressure, the electric resistivity will change. And here it's an example with the same case with the old contact law we used last year that was dependent only on temperature, and we obtained completely different geometries. Here we can see better for this same case how this problem is sensible to the electric resistivity. Same conditions, but just simply changing that, and we will obtain a different geometry. So it is really a key aspect to properly define the contact. And with this new law, it will allow us to have a better description, and it's actually easier for the definition, because it depends on the intrinsic parameters of the materials in contact. Now, the second aspect we have integrated is to use the optimization module in Forge in order to optimize the electric inputs for the process. In this case, so what we want to do is to go from this tube geometry and increase the head diameter. So this is a virtual shape that we want to obtain, will be like the intermediate shape. And what we do is to shedding a chain of simulations in which first we decide the electric input, the electric history. We run the simulation, then chain for a simulation in which we will take the results from the last one and put it in a position so that we can compare with the target geometry. And then the optimization module will decide how to modify the electric current input in order to get as close as possible to this final shape. Here we can see a classical setup of the optimization module that we have adapted for this process. So we go through some TF files for the same ones that has been used for the thermal change. We have introduced the electric parameters here. And then here also, for the second simulation, we decide our file defining the objective geometry. So now I will let my colleague Sergio talk about the experimental research.
Thank you, José. My name is Sergio ACEVADO. I've been working in this project with Transvalor for 2 years at the University of Osnabrück. At this point, at the very beginning of the project, we had to bring this process back into business. We needed to make it flexible and profitable. And we aim to design and optimize the process settings with the help of a FEM software solution. We needed to enhance the machine technology, and we collaborated for these 2 years with Transvalor to develop this tool. In the very first stage of the project, we developed a set of experimental tryouts. We gathered data, we recorded important parameters of the machine, the kinematics of the tools, the input and output power of the transformer, as well as the pressure in several points of the machine. We then built simulations based on this data, and then we use some of the parameters to verify these simulations, and as well as the geometry, for example, the geometry of the final piece, or in this case, the pressure of the tools and some electrical parameters. So we started the closed-die forging of a round bar made of C45 steel. We also evaluated the open-die forging of the same material. The tests were performed in the facilities of our partner IFUTEC, located in Karlsruhe in Germany. And with the data that we gathered, we carried out extraordinary simulations and obtained really accurate results, as you see. And we presented those in last year's Forge User meeting, as well as in the last ESA4 conference in Dublin, last April. So in the second phase of our project, we have moved forward, and we have modeled the process in Forge prior to the experiments. We also chose to study a more complex geometry. We simulated the free forging of a tube made of inox steel. We then wanted to deform this tube in the geometry you see displayed, and use this data as the input for the machine. Both results are valid results, are comparable, relatable. The geometries are pretty the same. The parameters of the machine were obviously what we get from the simulations. However, we were not able to achieve the final geometry we wanted, just running simulations in a common series. We couldn't find the very relation between kinematics and power input to deform the piece as we wanted. So at this point of the project, we have studied all the most influential variables of the electrical forging process. We have analyzed them within Forge and tried to obtain an optimal combination of them. However, there are so many parameters that are interdependent and time-dependent that we were not able to success. So that's why we turned to the news to implement this case in the optimization module of Forge, with which is possible to obtain the machine settings just by running an optimization simulation based on the desired final geometry of the workpiece. I would like to go back now to my colleague, José.
Yes. Thank you, Sergio.
Okay.
So, after several tryouts, we're able to set an optimization batch from which we obtained some rather impressive results. In the first place, the optimization gave us a geometrical configuration that was actually quite close to one of the, as you saw before, to the one obtained in the experiments with almost the same electric input. I mean, we set as target to optimize the electric history, and we obtained almost the same value, the constant value that was used in the experiments. And even though we didn't target for this geometry, it was obtained as one of the results of the optimization. And from this result, we will learn that we might need to improve the description of the friction used for the simulation, but the results are already quite satisfying. Then, in the same optimization batch, we're able to obtain a proposal from the optimization module that tells that if we use a step signal, we might be able to obtain a shape that covers the geometry that we desire, and it's supposed to minimize the amount of material that we'll need to remove afterwards, because we got quite a large range of geometries, and this was the best one we obtained from the optimization. So now we need to test feasibility of this configuration and this input in the machine they have at IFUTEC. So to finish, I would like to do an overview of the project evolution. In the first phase, we implemented the new a newly fully parallel 3D electric solver in Forge. And at the same time, Sergio and his team, they were working on setting the experimental machinery. Part of this work was presented last year in the Forge International User Meeting. It was carried out on the C45 steel. For the second phase, then they at IFUTEC, they were improving the machinery with new equipments in order to measure, to have better measurements of the inputs and the results, the displacements we obtain in order to have a good description of the process. And this work was presented as in the ESA Forum Congress 2017 in Dublin. And the last phase, so we were doing some tryouts with, this time with Linux. We introduced the new contact law. We were able to use the optimization module to study the process and in order to have a better idea how to run the model. And then there are some more things to come, because Sergio will continue his project in a PhD from next year on.
Hopefully.
Hopefully. So if there are three main ideas to get from this presentation. So now the electric solver is fully integrated into the new Forge version. What is missing is an interface, but we can use it as it is. The new contact law for the electric contact, even though it seems more complex, all of this is inside the solver, and actually simplifies the definition, because if we don't want to take into account a film between the bodies, we can simply use this law that will take into account the intrinsic parameters of the materials in order to compute an electric contact. And finally, the optimization. We're able to use it and quite satisfied with the results, and we can see that it allows us to study this complex process. So thank you very much. If you have any questions, we're pleased to answer.
So now, the first question.
Okay, thank you. Thank you for the nice presentation. I think it was a nice study. My question is related with the optimization. Yes. Have you checked the transferability of the data that you produce? How can you be sure that this is unique physical data for friction and other things that you determine by optimization?
When do you say unique, what do you mean, like?
In optimization,
Yeah.
you can get good results if it's possible because you are fitting to the experiments.
Yes.
But if this is physical, this should fit to another problem too, which is not the same problem.
Well, for the moment, we have carried out the studies only with their case because it's the case we have as reference.
Yes, we have the limits of the machine. The machine has some features. We simulate within the boundaries of the machine features.
And also, we have tried to study some cases from like scientific articles, but there's always some data missing from these articles. So it's quite difficult. For this process, we haven't found such, with this project, now we know that we have enough data to compare these results, but it's true that we could compare with some others. The problem is, we don't always have all the data. For instance, I tried with an article, they were describing just a few rheological data, but we didn't have enough information. So it's difficult to compare with other results.
Okay, thank you.
It's always the same limitation.
Okay, thank you.
You're welcome.
Any other questions?
It's David Evin from Forcia. Does it mean with this new feature in Forge that I could maybe imagine simulating spot welding, for example, with taking into account the Joule effect?
Yes, we are
in
working
Forge,
on it.
I mean, not in Transweld, but or some kind of spot welding simulation at least?
We're working on the spot welding and capacitor discharge welding, but the commercialization of it's something to be seen in the future, but it's already feasible, something we're working on.
The answer is simply yes. And the point is that, once again, let me take this opportunity to illustrate the benefits of mixing all of activity within the same event. This is exactly to answer this kind of question. We're going to have a presentation. I don't remember all the agenda by heart, but I think it's tomorrow about mechanical joining. And in this session, we will illustrate what we are able to do right now on spot welding. And so whatever the brick is, whether we're talking about forge, whether we're talking about Thercast, it has nothing to do for spot welding, but about transweld, whatever the solver in behind is, our purpose is to provide solution for assembly process. And spot welding is definitely one of the targets, and we will address it basically with this technique.
Mm-hmm.
So we will talk in the very near future about spot welding more in detail.